Hello everyone, my name is Gus Favor and my project focuses on building a business intelligence model to predict loan default risk before a lender approves an application. The goal is to help financial institutions reduce losses, improve portfolio quality, and make more data-driven decisions. The data set I'm using came from the Public Lending Club dataset, which contains roughly 390,000 borrowers' record. It includes more than 28 variables, such as the loan amount, the interest rate, the loan term, the income, the credit indicators, and loan status. But my target variable is the loan default, where 1 represents a charged-off loan and 0 represents a fully paid loan. The bar chart to the right shows the overall distribution, where about 80% of the loans are non-default and 19.6% are default. This imbalance highlights why accurate prediction is important. This project integrates 4 major statistical methods. First is the applied probability, where I calculated the joint and conditional probability to understand factors associated with default, such as the income level, the interest, the loan purpose, the default by states, and this helped me identify early risk pattern. Second is the statistical inference, where I used sampling distribution and confidence interval. I estimated population level behavior for variables like interest rate and default proportions. For example, the sampling distribution of interest rate produces a smooth bell-shaped curve with a 95% confidence interval. Thirdly is the hypothesis testing, where multiple formal tests were performed, including the Welch t-test for interest rate differences, the chi-square test for home ownership verification status and income group, and lastly the proportional test for high DTI borrowers. And it showed that all results were statistically significant, showing these traits meaningfully affect loan default risk. And lastly, for the regression model, I built 4 logistic regression models, including interaction terms. Model 4, which is the DTI and home ownership interaction, performed best with the strongest pseudo R-square and AIC values. And after I tested my model, I had an accuracy of 80.2%. To select the right modeling approach, I compared linear regression and logistic regression. The graph to the left shows linear regression fails because it predicts continuous values and not probabilities, and can go below 0 or above 1. This makes it incompatible with a binary outcome like loan default. While the graph to the right shows logistic regression, which produces an S-shaped curve, which correctly models probabilities between 0 and 1. It handles binary classifications and captures how the chances of default increases with interest rate. This comparison just confirms logistic regression is the appropriate approach for this BI model. To summarize, my business intelligence goal of my project was to design a practical solution that reduces financial losses and strengthen lending decision. A large borrower level data set with income, credit behaviors, loan structure, and demographic information was used, and I combined probability analysis, statistical inference, hypothesis testing, and logistic regression to build a predictive model that is both explainable and actionable. This model help flags high-risk borrowers pre-approval. It improves underwriting and pricing decision. It can help reduce charge-offs. It can strengthen portfolio stability and support data-driven lending policies. In conclusion, my BI solution gives financial institutions a measurable evidence-based way to control risk and improve long-term financial performance. Thank you for listening.